Boys, welcome to part 3 of the networks unit. Today we're going to talk about paths and circuits and the different types that you will actually see in this unit. So first of all, a circuit, or you might even see it called a cycle or a closed path, is a path that starts and finishes on the same vertex. Now there's certain rules around these, but just as a little quick example, as long as it starts and finishes on the same vertex, that there, what I've just drawn, we call that a circuit or a closed path. And that's what you need to know. It starts and finishes on the same vertex. Now, a Eulerian path is a path that uses every edge once and only once, but doesn't finish at the starting vertex. Whereas a Eulerian circuit is a path that uses every edge exactly once and does return to its starting vertex. Now, we're going to go through a few examples of these, of Eulerian paths and circuits. But another couple of things that you need to know is that Eulerizer graph means to add edges so that a Eulerian path exists. You're going to get some questions surrounding that. And then, whilst we're going through these couple of examples, there's a few things that we need to know straight away to do with Eulerian paths and circuits as well. The first one of them is a Eulerian path exists if the graph is connected to all of the vertices and they are of an even degree except for two of them. Okay, except for two of them. So let's have a little look at this top left one. The degree here is 3, degree here is 4, degree here is 2, and degree here is 3. So we are going to say that yes, a Eulerian path probably exists here. Remembering that the Eulerian path uses every edge once and only once, but doesn't finish at its starting vertex. Looking at the green point here, one of the vertices is of an odd degree, has to be the starting point, and the other vertex of an odd degree is the finishing point in a Eulerian path. So let's say if we start here, then here has to be the end point. So let's just have a go at it. I'll start here, so there, 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 there. Every edge has been used. I started here, I finished here. Down the bottom, if all of the vertices are of an even degree, then a Eulerian circuit exists. Right, now let's have a look at this one. There's 2, 2, 2, 2, and you can see that in here all of them are 4. So that means in this graph a Eulerian circuit must exist. Let's have a go. If you just follow on, look at that. All of the edges have been used and we started and finished there. There's one more example here that we're going to go through. Degrees of each, remember we've got to work out. Okay, there are 2 that are odd. That means if we start at one, we will finish at the other. Started here, finished here. There were 2 of them odd, so we knew that a circuit must not exist because all of the vertices have to be of an even degree for a Eulerian circuit. All right, a couple of examples of this. Well, if we just go through these and we again go to them, you'll realize that straight away there are more than 2 degrees of the vertex that are odd, so this one cannot have a Eulerian path or circuit in it. Let's have a go at this one. There's 4 there, 5 there, 4 there, 3 there, 2 there, and 6 there. Wow, that means that 2 of these are odd. If we start at one, we will finish at the other, and a Eulerian path must exist in here somewhere. Let's start at B. Look at that. Every edge has been touched. We started here, we finished here. Hamiltonian paths and circuits are a little bit different though. Hamiltonian paths is a path that passes through every vertex exactly once and doesn't return to its starting vertex. So they don't actually touch every edge compared to a Eulerian path. This one just touches every vertex once. A Hamiltonian circuit, much like the circuits we've spoken about, they start and finish at the same vertex. But again, Hamiltonian circuits, they touch every vertex, but they don't necessarily touch every edge. Let's have a couple of examples. All we need to remember is you just have to touch every vertex. Okay. Obviously, a Hamiltonian circuit exists in there. In this one, that is obviously a Hamiltonian circuit, starting and finishing at the same point. And in this last one, we'll see if one exists in here. Yep, a Hamiltonian circuit is also in there. Weighted graphs have numbers allocated to each edge. These numbers or weights may represent distances, times, numbers of cars traveling down the street, and so on. So if we have a look at these, let's say if we want to go from A to B to C to D, we can actually see how many cars are on those streets if we call each of the edges streets. So A to B, there was 6. Obviously they wouldn't be cars because there's 3.5. Then down to there. And we can actually work out the weight of that, the route that they've taken. So it'd be 6 plus 3.5 plus 5.5. You could maybe call it kilometres rather than cars on the street. What's that? 8, 9, 15 would be our answer. So it'd be 15 kilometres from A to B, B to C, C to D. What would we call that? Well, that would be a Hamiltonian path because we've touched every vertex, but we have not used every edge.